Whereas it's our first time really getting into this calculus quite a bit, I'm going to try to do it a little bit slowly for you. There's a situation where you've got yourself a switch and a resistor and a capacitor in the same circuit. And my people, they call this an RC circuit. Why? Oh, resistor and a capacitor. Okay, and maybe even simpler though would be just a charged capacitor. We'll put some Q here and some minus Q here, and we'll get ourselves a resistor, and then we've got, what do we have to have? A switch somewhere. Let's put a switch right in there because we almost ran out of space. So when I close the switch, the charge will move. In fact, a current will flow that direction. This is what would have happened if we'd allowed that to charge and then taken out the battery. Then we close the switch, and the capacitor will discharge. And I want to try to figure out how the capacitor will discharge. I know by Kirchhoff's loop rule that, well, no, sorry, the junction rule, that the current here has to be equal to the current there. At any instant, current through the capacitor has to be equal to the current going through that resistor right there. And if I could write that on an equation, I would say the current through the capacitor plus the current through the resistor would have to be equal to 0, or maybe a minus sign or something. Nah, we'll just leave it like that. Now, the current through a capacitor is really the derivative of the charge on the capacitor as time changes, right? And the current through the resistor is really just V over R for that resistor. So that's going to be equal to 0. And the charge on the capacitor is C times V. So I've got d CV. Don't talk to me about partial derivatives. I'm going to say that the capacitance is not changing. So I'm going to take that out of the derivative, and I'm going to have C times dV dt plus V over R equals 0. I can solve this. Ooh, what's the easiest way to do this? Now, let's just forge right into it. I'm saying that I can then say that dV over dt is negative V over C times R. Are you still with me? Or oftentimes it's written as R times C. Huh. Yeah, see that? And now my plan is to do some separation of variables and such, and then maybe I'll differentiate it or integrate it or whatever it needs to happen. I'll probably integrate it, actually. I think I'll get dV over V is negative dt over RC, and I think I'll integrate both sides of that equation right there, leading to a lovely integral that says that the natural log of voltage is, well, negative t over RC plus some constant. I got to make one of these fuzzy, see? There. That's a fuzzy C because it's not the capacitance, it's a random constant. Probably depends on the initial conditions, and I'm going to call these initial conditions V naught. That's the initial charge on, initial voltage on that capacitor. Over here, this I'm going to call V battery, and if we had in fact charged this capacitor with that battery, then V naught would probably be pretty close to V battery if we allowed it to fully charge, which would take forever, which is a long time. But my point is, if we then exponentiate both sides of this sucker, we will get the voltage as a function of time is the starting voltage times e to the negative t over RC. And this is also often written as V naught times e to the negative t over tau. That's right, we introduce a new variable and we call it the time constant. Tau is time constant. And the time constant is cool. Let's look at this function for a little bit. It says that the voltage will be decreasing, and it says the voltage will be decreasing in a way that if you've done any cool labs recently, you will probably find to be like that, very quickly early on and asymptotically to 0, never quite reaching it, starting from V naught though. So the beautiful thing about exponential functions is that when tau equals t, then v as a function of tau, that's at the time tau equals t, then I would get that to be V naught times e to the negative what? e to the negative 1, which is v naught divided by e. Turns out that 1 over e, which is what I'm going to be doing to my v naught, 1 over e is approximately, what do we get, 37%? It's 37%. That's cool. So when this voltage gets to 37% of its value, right there, we can say that this time is tau, and tau is simply RC. So if you're interested in making the capacitor discharge more quickly, you put a smaller resistor in there, right? So then this whole graph shrinks up to the left. If you want a larger resistor in there, then you're going to magnify the whole graph out to the right, and you're basically changing tau, the time constant. Some people might be more interested in charge. If you want the charge instead of the voltage, well, you know that Q is CV, so all you're going to be doing is multiplying this by a C. C. Because it's a constant for the capacitor, you're going to get the same result. The only thing that needs to be said further, wait a second, there's something else that we could also say. If Q is CV and I is dq dt, then really we're talking about C times dV dt. So current in this sort of a situation is the slope of our voltage line. Oh, dang, that's beautiful. I love this stuff. Not only that, but I also want to point out that we could solve this situation right here. It's not so different in the charging. Instead of a graph that looks like that, we're going to get a graph, if you're charging, you're graphing voltage as a function of time. It will be approaching, the voltage across the capacitor will be approaching the voltage of the battery, but it will start from 0 and it'll go really quickly early on, and it will asymptotically approach V battery, reaching it a long time from now. And I guess it will get to, what, not 37%, but probably 63% at a time that's equal to tau, depending on R and C. Bigger capacitor means longer time to charge that sucker up. Bigger resistor means longer time to charge that sucker up. So if you want to charge capacitors quickly, get tiny capacitors and reduce your resistance. But that's not always an advantage, because then it's harder to study it. And maybe you could blow stuff up. But be careful. And the equation for this is probably going to be V as a function of time is, oh gosh, we're going to have to do something like 1 minus this decaying exponential, negative t over RC. Remember, a lot of people call that tau. And then I'm going to multiply that by V battery, or V naught. So initially, you've got a 0 here. So this is e to the 0. E to the 0 is 1. And 1 minus 1 is 0. So I don't even care what V battery is. Your initial voltage is 0. What if I plug in infinity here for this time? This is e to the minus infinity, and everything to the minus infinity is 0. So then I'm taking 1 minus e to the minus infinity, which is 1 minus 0, and that's just 1. And that says that at a time of infinity, but you really do have to wait that long, you're going to find that the voltage on the capacitor is the voltage of the battery. Lot of great physics here. Have a good time.